Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture in the course on energy resources, economics and environment. In this class, we will be focusing on energy and environment and the environmental impacts of energy systems. In the last lecture, we looked at the energy flow diagram and we saw how whenever we want to use energy, the final energy that we use in terms of the energy service or the end use activity, in order to get that, we have the primary energy, the energy that is available in nature, which goes through a sequence of conversion steps before we get the final energy service. So, at each of these steps, some amount of energy is used, and in using that energy, there is also some adverse impact and there is an environmental impact. So, we are going to try and look at this. We also saw in the last lecture, we looked at the whole phenomena of growth and we looked at the world having a tendency to grow. We have everything in terms of the population grows exponentially and all other parameters follow that exponential pattern. So, when we look in terms of the water use or the energy use, we said that there would be exponential or unbounded growth. When we look at unbounded growth, the area under the curve, when we take it to infinity, is infinite. So, when we think in terms of a finite resource situation or a finite ability of the world to maintain and to look at the waste, that becomes a problem. So, the whole issue is when we design energy systems and these energy systems grow, what are the kind of impacts that happen to the environment and are these impacts going to be sustainable into the future? So, the issues that we are going to discuss in the section related to the environment, the first one is why is the environment important? How do the energy systems impact the environment? Is there a trade-off between environment and economic development? What are the major impacts and causes? How do we quantify these impacts? And how do we ensure a sustainable future? So, we will take a quick snapshot of why the environment is important to us, what is the impact of the energy systems on the environment, and how do we do this quantification. So, if you look at this figure is from the book by Tester on sustainable energy. When we look at an energy system, we are talking of either exploration or production or conversion or utilization, and in doing that we are using some natural resources, we are using some human resources, and in the process we are then generating, we have the useful effect that we want, which is for instance the cooling or the heating or the transport. So, there are useful goods and services, but in producing that there are unintended impacts that we cannot avoid. And these impacts, some of these are listed here. So, you have solids, liquid and gaseous effluents or pollutants which go out into the atmosphere, into the air, into the land, into the water, and each of these, depending on the concentrations, depending on how you treat it, how you send it out, will have different kinds of impacts either on humans or on the ecosystem. Then there is ionizing radiation, the electromagnetic radiation, aesthetics. In many cases, for instance, when you have large wind turbines and you look at these wind turbines in the landscape, it affects the patterns of birds and it affects the aesthetics. Several local communities are not necessarily in favor of this, and so this also can create problems. Many of these situations, when we use a certain amount of energy, we also reject some heat which is a waste heat, and this causes, for instance, when you have cities and you have a concentration, you have an urban heat island effect, where some portions of the cities would have much hotter temperatures, and then there are ways in which we try to mitigate this. Sound, for instance, if you look at a large compressor or you look at a power plant, there would be a sound, and that also has an impact and on humans staying in the vicinity. Electromagnetic radiation. So these are all these unintended impacts, and these are the impacts that we need to quantify. Typically, the way this happens is that we start with using the energy system, and we start using more and more energy to make our lives more comfortable. Many of these problems then get into they accelerate, and it gets to a level where the problem is seen as a problem that needs solutions, and then we try to modify the energy system. So this is the way in which it happens. So for instance, if we look at typically when we look at all the energy that is being consumed, if we are looking at fossil fuels, which is today the present mode of energy consumption, whether it is coal, oil, natural gas, the bulk of our energy use today is still from fossil fuels. And if you look at the use of these fossil fuels, we have the pollutants, or we let out these gases into the atmosphere. And for instance, there are sulfur dioxides. This happens through industrial processes. This sulfur dioxide also comes in the power plants. Nitric oxides, again from power plants and industry. Carbon monoxide from vehicles, as well as from industrial processes. Solid particulate matter, and in this particulate matter, it's also important to see what is the size range. So we talk of PM 2.5 and PM 5. The smaller the particle size, the larger the impact in terms of health. And so we monitor some of this, and this is one of the things which is contributing to air pollution and urban air quality and respiratory health impacts. Carbon dioxide and chlorofluorocarbons, and we will talk about this, these are global pollutants. So all of these have different kinds of impacts. So one is it's modifying the atmospheric properties of processes. In the case of sulfur dioxide and SOx, it combines, and then it can cause precipitation acidity, which is called acid rain, and that can corrode variety of equipment. There can be smog, photochemical smog. It can affect visibility. So for instance, on days where you have a navy day and you are trying to see out into the ocean, often there are restrictions in terms of vehicle movement, so that the visibility can get improved. And corrosion potential, radiation balance alteration, we'll talk about this a little more in detail in the CO2, and ultraviolet energy absorption. So the impacts can be at the local, regional, or the global scale, and these are just some examples of some of the air pollutants which have an impact on the environment. So the adverse health impacts can be going from mainly based on local, and we can go from local perturbations to global disruptions as the human energy use increase. In the early 80s, Professor John Holdren of Harvard University proposed an index called the Human Disruption Index, and this was to look at what is the disruption at a global scale of a particular pollutant. This is defined very simply as the ratio of the human generated flow of a given pollutant to the natural or the baseline flow. So the idea is that in case the human generated flow of a pollutant is orders of magnitude less than the natural or baseline flow, then nature has the ability to manage it, and nature will have the system, it will not show up as a problem. But the moment it becomes of the same order of magnitude as the natural or baseline flow, then there are problems, because then the human impact is something which nature is not able to regenerate or absorb. And so if you look at these ratios, These were the human disruption indices which were tabulated by John Holdren, and you will see that the disruption index, lead emissions, oil to ocean, cadmium emissions, sulfur emissions, all are greater than 1. And you will also see on this side that a large percentage of this is because of the energy sector and the energy use. So energy and its impact, the current way in which we are using energy has an adverse impact on the environment, and this is why we need to change the way, look at efficiency, look at ways to mitigate. Nitrogen fixation, again if you see DI, mercury emissions, nitric oxides, particulate emissions, carbon dioxide, and you can see all of these are showing up as problems because the human disruption index is greater than 1. So we go forward in this, in that if you look at the energy flow diagram that we discussed, at each element of that energy flow, wherever there is a conversion, there will be associated with it some emissions. So if you look at electricity which is being used in the household, in order to get that electricity, we start with the mine. If it is coming from coal, it's the coal that we are mining. So at the mine itself, there are some emissions which are going into the land and the water. There are emissions which are there in the air pollution. Then that mine goes to a coal bay, there's a transport, and that has some emissions. Then it goes to a facility where you are beneficiating the coal. Again, at that point there are some emissions. The transportation has associated with some emissions. Then you have the power plant which has the bulk of the major emissions, and then we take it to the transmission to the household. So you can see that we have to calculate the emissions over the entire cycle of use, entire fuel cycle. So just like we looked at the total energy use, we can look at the total emissions. So now the question which arises is, what is safe for humanity? What kind of regime is safe for humanity? And a group of researchers led by Professor Rockstrom worked on this, and there's a paper in Nature which I would urge you to read, which was published in 2009. It's called the Safe Operating Space for Humanity. So what the researchers did is they looked at a large number of different parameters, and they looked at what were the natural equilibrium for these parameters before we started industrial activity. And then based on that, they also identified through some models that how much, what is the limit for that criteria. So with that, they identified a set of 9 different criteria which were critical for humanity to operate within a certain safe regime. And in those 9 criteria, they identified 3 where we had already exceeded the limits. So I will suggest that you look at this. The paper starts off by saying that the history of human development has had a number of different eras, and if you look at the history of the world on a large time scale means we are looking at thousands, 100,000 years. So the axis which is there on this graph is starting from here 0 to 20,000, 40,000, 60,000, 80,000, 100,000 years before. And in this we are trying to see what is a stable environment for the Earth. As far as we know, the Earth is the only planet where there is life. And this is because we have the atmosphere which maintains the temperature constant at a particular value. Seen here is an isotope of oxygen, which is a proxy for the average temperature. And if you look at this, you will see that in nature, we've had different kinds of eras, and in all of these eras, there has been a significant fluctuation in the temperature and the climate. It's only in the last 3,000-4,000 years where we've enjoyed a relatively stable environment, and this is the period where actually life evolved and the civilizations evolved. This is called the Holocene, and this is the period where we've had significant growth and we've had significant development and improvement in humankind. This is now threatened by human activity, and geologists have coined a term where this is called, now we are now going into the Anthropocene. Anthropocene means this is an era where it is human activity that is dictating the changes which are happening on the earth and on the earth's climate. And this Anthropocene, it has been shown that is not something that it is going to be sustainable into the future unless we make some changes in the way we develop and operate our energy systems. So, in this paper they look at a number of processes at a planetary scale, and 3 of these processes are climate change, ocean acidification, the stratospheric ozone, and there are also aggregated processes from the local and regional scale, that means chemical pollution, biodiversity loss, land use change, freshwater use, atmospheric aerosol loading, global phosphorus and nitrogen cycles. And in all these cycles, you can look at the paper for details. There is a proposed boundary, there is a current status, and then there is a pre-industrial value. So, for instance, for climate change, the pre-industrial value is 280 parts per million by volume of CO2, and the proposed 350 parts per million by volume. And current status has gone up. And in this, if we look at it, this is a graph. Shows you where we are exceeding the limits, and you can see that we've exceeded the limit on the rate of biodiversity loss, the nitrogen cycle, and the climate change cycle. And we will discuss the climate change cycle in a little more detail. So, in the case of CO2, as I mentioned to you earlier, as we know, the only planet where there is life is the Earth, and the reason for that is a thin layer which is the atmosphere, and in the atmosphere we have the main constituents are nitrogen and oxygen. Carbon dioxide is actually at a relatively lower concentration, but carbon dioxide has an important parameter which is a radiative forcing. So, carbon dioxide actually permits the incoming radiation to come in, but traps the outgoing, with the result that it increases the overall temperature, and the radiative balance created by the CO2 concentration results in an average temperature of land and water of 15.5 degrees. If you look at a greenhouse, you will find that in a greenhouse, because the greenhouse traps the outgoing radiation and does not permit it to go out, the temperatures are higher, and this improves the growth of the plant. So, in a similar fashion, if the CO2 concentrations increase, we will have a temperature rise on the surface of the earth, and this will affect the climate patterns. You can look at the evidence. Of course, there is a natural variability, as we saw when we looked at the thousands of year time horizon. You can look at the evidence that is there on the IPCC. There is an intergovernmental panel on climate change, www.ipcc.ch. You can look at that site. There are reports on the science and the technology options and on climate change, and that will give you all the evidence. Now, if you look at this graph, you can see that CO2 is a critical gas in terms of radiative forcing. The others are CH4, nitric oxide, and then there are other effects of aerosols and moisture. So, we are basically going to focus on CO2. This graph shows you the time series evolution of carbon dioxide in the atmosphere. Now, this is for a 1000-year time horizon. The first question that may come to your mind is that was this a problem over the last 1,000 years, and how have we been tracking it? So, the earliest initial mention of this problem of the carbon dioxide and climate change problem happened in 1950s, and only since the 70s there has been serious efforts in the IPCC. So, when we look at a 1,000-year time horizon, this record is something that is actually available to us in nature. So, if you see on this graph, on this side you have this image, we have these expeditions to the Arctic and the Antarctic, where scientists actually go to the ice cores. So, typically when you look at in the ice which has been formed at depth, that ice has been formed at different periods of time, and based on the isotope of carbon, one can actually identify what is the age of the ice based on the depth. Once you look at the age of the ice and you have the ice core, the air which is trapped at a particular depth is the air which was there when that ice was formed. So, we have the year and we have the air. We can look at the composition of the air, and that will give us a frozen record of what was the CO2 at that time when that ice was formed. So, you will find, if you just Google, you will find many different expeditions, and all of them have a similar kind of plot. So, if you look at this plot, on the x-axis, it is the age of the air. So, we start from, let us say, 2000 and going back to 1000 when 1000 AD when the ice was formed. So, at different depths, this will be at a higher depth, and on the y-axis is the carbon dioxide mixing ratio, what is the percentage of carbon parts per million by volume of CO2. So, that gives you the CO2 concentration in the air. And if you look at the first from 1000 to about 1800, around 800 years, you will see, if we got this kind of data in a laboratory experiment, we would say that this is more or less constant. It's a process under control. There is some variation, but it is within plus minus 5 ppm. So, you see this level, this straight line that we draw here is at 280 parts per million by volume, and this is the pre-industrial equilibrium of CO2, and this is what the earth can take. Then what happens? You will see that it's almost like the second curve which I have shown here. This curve has a different trend completely. This curve represents the trend that we had seen in all these other cases where we have population growing exponentially, anything that humans are consuming growing exponentially. So, this has an exponential growth trend. So, clearly there is a diversion from the equilibrium, and what happens here? So, this is the point where we had the industrial revolution. We had James Watt and the steam engine, and we had the use of coal to develop industry, to create mines, to have power, and this is where we started using more and more coal and more oil and natural gas. And so, we have two things. We have the fact that CO2 has a radiative forcing component, and that all life on the earth depends on the equilibrium temperature. The radiative component with an increase in the CO2 concentrations would imply an increase in the global temperatures, and this is what is called global warming, and this will result in climate change. There are large scale models operating where you can try and figure out what will be the impact. There are uncertainties, of course, in the model, but what is reasonably certain is that in any case this is a disruptive effect which we need to mitigate, we cannot continue with this kind of exponential growth of the CO2. Now, to look at this in more detail, there has been, from the 70s, there has been a trend of actual measurements in an observatory at Mauna Loa in Hawaii in the US, and you can see this on this graph. You can see, and you will see when you look at this graph, you can see very clearly that it goes through ups and downs. Now, when you observe this carefully, you will see that one crest, that is the peak, and one trough happens every year. And this is how, but overall there is a sort of exponential growth, but it goes through a trough and then a crest. And so this is this peak. Now the question is, why do we have this seasonal kind of variation? We have a number of reasons which you can think about. Is it because the CO2 concentrations show an increase over several years but fluctuate randomly within the year? Or the seasonal fluctuation in the CO2 concentration is due to seasonal fluctuation in the energy pattern? Seasonal fluctuation is due to local fluctuations in Hawaii? Seasonal fluctuations are due to ice melting in summer, or none of the above? So if you think about it, you will find that, well, this fluctuation is not random. There is clearly an increasing trend, and clearly there is an annual pattern. So it's not the first one which is true. The second one which you think of, seasonal fluctuation in the CO2 concentration, is due to seasonal fluctuations in the energy pattern. If you want to check whether this is true, look at annual energy use over the globe and see whether that changes over the seasons. And you will see that there is a trend of increase over the years, but there is no clear-cut seasonal pattern. So this also is not true. This is a CO2 is a global pollutant. It is not due to local fluctuations in Hawaii. If you did this in some other place also, you would get the same effect. And ice melting in summer does not create enough of an impact to be able to show this. So the answer actually is none of the above. The reason for this is because of the trend in the growth of the vegetation, and there are deciduous trees which will grow and grow in a particular season, so that the CO2 sink increases in a particular season and decreases when there is a fall, and because of that growth and the CO2 absorption capacity vary, we see this kind of trend. Okay, so let us move on. There is a website, you can look at that, and I looked at this number in recently in the month of June in 2019, but you can go to CO2 now and you can see the CO2 concentration. So we said 280 parts per million by volume was the pre-industrial. We are already on this particular day, the average is about 415 parts per million, much above the norm that we've set in terms of 350 parts per million. And so this is the problem that we need to mitigate. We have a situation where we have an energy system which is having these kind of CO2 emissions. Now when we look at we talked about the 280 parts per million by volume as a natural process and something which is coming through an equilibrium. So we can look at the carbon balance. There is this paper in the annual review of annual research of Earth, planetary Earth, and in these annual reviews you can see that there is the carbon balance. There is already carbon in the fossil fuels, there is carbon in the ocean, and then there are flows. And in the flows that we are talking of, there is an equilibrium in the atmosphere, and then there is a flow which is coming in through because of decomposition, there is respiration, and then there is human generated activity. So in this carbon dioxide and carbon balance, it is the human activity which is causing the imbalance, which is then related to the change in the concentration. And this is something that we need to try to mitigate. So the indicators of the human influence of the atmosphere, again this is from the IPCC report. You can see we talked about CO2, but we can see that similar kinds of things are visible when we look at methane, nitrous oxides, we look at sulfate aerosols. So these are all human generated impacts, and these are things where as we design energy systems, we have the option of redesigning the energy system, or we have the option of mitigating, trapping it, capturing it. So these are some of the things that we, and we talked about the radiative. This is another from the IPCC, another figure which shows you the kind of radiative forcing components. Different pollutants that we talk of have different lifetimes in the atmosphere. So it is not just about today's pollution. If you are looking at CO2, it lasts in the atmosphere for about 100 years. So it's a cumulative effect that we need to calculate, and that is this is captured in the form of a global warming potential. CO2 is considered to be 1, and the equivalent value for all the other gases is converted, and these are the numbers. So what happens is that some of these, like SF6 and the chlorofluorocarbons, have significant global warming potential. So even though they may be at much smaller or trace levels, they may have a greater impact. So everything which is calculated in the case of global warming is usually done with the CO2 as a baseline. So when we talk about CO2, we also talk about CO2 equivalent, and we take all the other gases and convert them into CO2 equivalent. So whenever we talk in the course, we will be mainly talking about CO2, but please remember this means CO2 plus the equivalent of CO2 from other gases which are also creating global warming. So now let us look at any pollutant. We would like to see what happens when we have a fuel, and that fuel is being used in a device. That device gives you your useful energy, and then we have some emissions. So if we look at a vehicle, these emissions will go in the place where the vehicle is moving. If we look at a power plant, these emissions will be there in the location of that power plant. These emissions, now this is one device, in that area there will be other devices, D2, D3, Dn. There are different things. So all of these emissions will come together, and then you would basically get a concentration. So if you look at, for instance, in the city of Delhi, you look at a number of vehicles at a traffic signal, each one is emitting some particulate matter. We will take all the particulate matter which is there. Now depending on the air velocity, some of it will diffuse and move out, some of it will remain there, and you will have a concentration. Now in that place, if there is a human, and that human is, you are in that place for a certain amount of time, then you will get a dose of how much of that gets absorbed, that will go to your lungs, and then that will have a health impact. So you see the chain, it's about what kind of fuel we are using, what is the composition. As we use it for useful energy, there are some adverse impact. That emissions, of course, if it is in an area where it gets diffused out, then it will not result in too much of a concentration. We can have a norm in terms of emissions cannot be more than this. We can also have a norm in terms of trying to see what is the concentration. For instance, in the case of Agra, because of the Taj Mahal and the kind of discoloration which was happening to the Taj Mahal, several industries were asked to close down and not use fossil fuels in the location, so that you could reduce the emissions and do that. So we can look at concentration and concentration norms, and if you see, you will find that these norms are monitored by environmental stations at different locations. So that will be a function of location. Then if you have people who are there, depending on the amount of time, you will have an intake, and based on that intake, then you can look at the impact which is there on respiration, it will have an health impact. So, if you look at this on this slide, you will see that this is illustrated in this is in from the energy after Rio. So, you have the fuel, you have the emissions, then you have concentration. That concentration results in exposure, and that exposure is dependent on how many people and how much time. That results in a particular dose, and then that dose results in an impact, and that impact could be could be fatal or could be resulting in a other health impact. Now, depending on the percentage of the emissions which are taken in, so for instance, active smoking is something where all the emissions are going in. So, it is like 1 ton per ton of pollutant, almost all 100% is going in. If you look at second hand smoke, if you are near a smoker, then you will take much less. In stove which is vented indoors, you have and this is indoor air pollution in a boiler, in a vehicle, in a coal based power plant. So, we can look at this and then we can see the impact and use it in our models to quantify safe levels, to quantify health impacts. The World Health Organization has created a parameter called the disability adjusted lost years. So, this is in order to, suppose we look at different kinds of impacts of different pollutants and what is the effect, and why do we want to do that? Because we want to quantify and see where we would like to put interventions, where we would like to put money, what kind of norms we need to have. So, what is this is defined as disability adjusted lost year is thought of as one lost year of healthy life. And then some of these dailies across the population or the burden of disease is thought of as a measurement of the gap between a current health status and an ideal health situation. Ideal health situation where the entire population lives to an advanced stage free of disease and disability. So, when we want to make this calculation, this is calculated as a sum of two factors, the year of lost life. So, for instance, if due to pollution or if due to, let us say, tobacco, there is a person dies of cancer at a particular age, we have an expected age which the person would have lived to, and the number of years that is lost is then computed into the number of deaths, and this is summed up. And in a case where it is not fatal, but because of that people have disability or they are unhealthy and they lose a number of days of healthy life and number of years. So, this is how it is added. This is then added by different categories and summed up, and then this is one way in which you can compare, for instance, indoor air pollution from stoves versus vehicle impact of outdoor air pollution in vehicles versus diseases like tuberculosis or malaria, and all of this can be used to see the impact and to then see what kind of norms we should do and then look at it. So, otherwise in many cases, for instance, if you look at smoke coming from chulas, the effect is seen over a long period of time. So, people may not immediately appreciate the reason or the motivation to go for smokeless chulas. So, this is a whole impact of energy and health, and this is something which one needs to compute when you look at different kinds of policies and different kinds of interventions.